This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kuyken. Clear Contributions. Let's have clarity.
All right, it sounds like everybody's got an issue with chirality centers, and that's understandable. This is a difficult thing to work with. Oh, good. Perfect. So tomorrow for your lab, what I'd like to do is I've got a little chirality center workshop kind of thing where you bring your molecular model kits and we just build all the different models of different molecules, and you can look at that. So since we're going to do a workshop, the 7 a.m. group come at 8:30, and maybe that room on the main floor here in Durham will be available still tomorrow, and then the 10 o'clock, we'll see if that room is available also. And we'll work it some more because this is really tricky and you got to see it a bunch of times before you really get it. So that's understandable if you're kind of floundering right now. What I thought we could do is put the naming stuff on the board just for double check and to make it go faster also. And then I'll go over the chirality problems with you. So it's L through T or something, L through S, L through S. And I forgot where I picked up last time, but oh, you're first. Okay. That's right. I came down the road this way and we ran out for you so that you get L, M, N, O, P, Q, R, S. No, because you finished up the stuff last time.
So speaking for the final all I do is how much way? Well, this is like really easy now.
Naming?
So I have a question.
Yeah.
Can you just explain to me this chirality before we go over to class?
Sure.
Perfect. So this is what it is. So I was under the impression that if you have multiple hydrogens attached to it, no bueno, right?
Right.
And if there's multiple, if there's any group that's the same, no bueno.
Right.
So this would not be a chirality center.
Right.
But then when it comes to this one, this I, no chirality center.
Right.
Then when it comes to this C, there's only 3 bonds connected to it. With that,
There's an implied hydrogen.
there's an implied hydrogen, and that would be a different group.
That's right.
And so that would be a chirality center,
That's
and this
right.
would be a chirality center.
That's right.
But then also when it comes to this one, no chirality center because there's multiple hydrogen.
Yeah.
And then one more question. Whenever it comes to... Right. Yeah, so that was my question. So if there's... These are the same group, therefore no bueno.
That's right.
Perfect, thank you.
You got it.
Yeah, I got it right. So these are,
My turn
so
is
these are,
last,
you
but
have
I
to
don't
just
have
follow
it.
the
So
Okay.
can Monty go in my
Sure,
place and
sure,
I'll go in his?
sure.
Okay, thank you so much.
You're welcome.
Yeah. Right. So this one's done because there's multiple hydrogen. Oh yeah. So there's multiple hydrogen attached, no good. These ones same group attached, this one not good. This one multiple hydrogen attached, not good. This one is actually not because of the
Are you feeling better today, Alyssa?
Yeah. I don't know.
Did you get to play?
Yeah, I did.
I think what it was with what she was talking about going with the straight line, that was just to see it more as in a natural standpoint, other than cycling, like what's easier. Does that make sense? Yeah. Perfect. This chirality seems pretty easy then.
Well, you changed your mind fast. Yeah, it isn't too bad.
Oh wait, actually, yeah, this F. When was this F? Is that a chirality stuff?
No,
It's not because
it's the same group coming this way as it is coming that way.
Oh shoot! Okay, that one's gonna be confusing. Never mind, I don't get it. Okay, no, so it's just the same group.
Yep.
Because look, if you look at it this way, it's a different group going this way than it would go this way. Does that make sense? Yeah. And this one, it's the same going this way. So if there were to be like another.
So this is the naming first, right? And we always want to name it 1 to 2.
That's right.
So then it has to go this way.
That's right.
Okay, cool. That's what I thought.
I think
Yes.
so. Because like this was she said, so if we were to draw this
It
out.
goes this way, right?
Right.
4 so it'd be 4 methoxyoxane.
True.
And then you put these guys. We'll put this guy at 1. Let's see, all right. And then this guy's gonna be at 3. 3. So then from there, second group here. I'd imagine it would be, but I don't know. I'm not. Well, then there'd be 2. Oh no, because this carbon's attached to it over here. This carbon's attached to it over here. So there'd be 1 hydrogen. I'm lost on the cyclos. That's what I'm lost on now.
That's easy to have happen. Any problems with L? Uh-huh.
It's the longest continuous chain, all of it, or you don't have the last 2 methods.
This here?
Yeah.
So you have to include the carbons directly attached to the functional group. You have to keep going one direction when you are tracing a line, so you can't come here and then go over here or something. So you gotta, when you come to this, you gotta go this way, or this way. You have to make a choice anytime you come to a branch point. There is one other issue though. Uh-huh. Oh.
Yeah, oh yeah, the methyl and the ethyl, it doesn't matter with, because you put the dye in afterwards and don't alphabetize it then.
Mm-hmm. So that's not it. Uh-huh.
With the ethyl, 2 instead of 3.
Nope.
You just have to.
What you got? That's right. This is not a cyclic compound, so you do have to say where the triple bond is.
Oh, okay.
Yeah. The only time you can get away with not putting a label on is if it's cyclic, or if there's only like 2 carbons.
Does it say 3 ethyl?
Uh-huh. 3-ethyl, 3,5-dimethyl hex 1-ine is correct. Okay. All right. How's M? Any issues? Looks okay to me. This has got the tiebreaker rule where you have 2 and 4 going either direction, and it's completely the same numbers but different substituents, and so therefore you go with the one that's first alphabetically. Mm-hmm. All right, N. Any issues? It's correct. The temptation is to do where you go 1, 2, 3, 4 so that you have a 2,4 dimethyl, but you don't care about that because if you had 2, 4, all you're looking for is the lowest possible number, not an average or something like that. 1 is the lowest number possible here, and so that's why you go with that direction, even though that gives a 5 to the other one. You don't care about what it does to any of the other numbers, only what's the lowest number possible. Okay, and O. Good? No? That looks fine to me. The only trick is picking the numbering direction, and that's pretty clear cut. Okay. P. Okay. Good. Q. Yep. Either way that you number, you're going to come up with a 3, 4. 1, 2, 3, 4. So because you have a tie in numbering for the functional group, now you go for the lowest number possible for a substituent. That's the first tiebreaker rule. So you'd actually want to number it this way, 5, 6, so that you have a 1 bromo, 4 methyl hex 3-ine, or hex 3-ene, I'm sorry.
Would not be 1 bromocyclopentane -1 ene.
No, so an ane ending means that you don't have any double bonds between carbons. And so if it's an ene, it can't be an ane. So for enes and ines, you drop the whole ane ending. All right. Okay, I've got 3 issues.
And the soda methoxy, and it's an ethyl instead of methyl.
There you go. Okay, and then you can just separate things with dashes, and that's good. Okay, RS. All right, anything here? Got an issue with. I think that looks good, huh? So this has to be your 1 and 2. So the only options you have are count this way around counterclockwise and then go this way clockwise, where this is 1, 2, 3, 4, 5. If you go this way, that has the number 5. If you're going this way, it's 4, so that's why you want to go this direction. You don't re-alphabetize by the die. You don't necessarily get the lowest number possible. I think first alphabetically. Those were all the kinds of things I think I was trying to like throw at you just to make sure that you stayed on track.
So why is it in this one that you don't give the 1 to the ethyl group, because it does come first alphabetically?
Okay, so that's the last tiebreaker rule where you have an exact match in all of the numbers for each direction that you're going around the chain,
Right, okay.
around the ring. Any other issues with that stuff? All right. One thing that I've done when I built these chapters is I have problems from all previous chapters at the end of a given chapter. So you're going to be able to keep practicing this. I have more problems at the end of chapter 2 and chapter 3 and chapter 4 and everything, so that you don't forget. You can keep refreshing. It seems like you mostly have it, and there's just a couple little issues that remain. So I do want to keep practicing you on it before the test, but I think you pretty much have the idea. So we'll go on to the chirality. Yeah. Okay.
How's your finger?
It still hurts. I still have a little bit of a hard time bending it, and it's still a funny color, and I'm running out of antibiotics, so I'll probably have to go back. Okay. So, chirality centers. That's where you have non-equivalent options for the stereochemistry of the molecule. because you have a carbon that has 4 different groups attached to it. And so that's something that you want to watch for when you're naming something, so that you can describe exactly how the stereochemistry is in that given molecule. So since you have to have 4 different groups attached, it's a total waste of time to look at anything where you have 2 or 3 hydrogens, because you automatically wouldn't be able to have 4 different groups attached. And you also don't want to look at double bonds or triple bonds, because those carbons can't have 4 different things attached since they have the extra, since they're using up one of their bonds or 2 of their bonds. And so when we went through these on Friday, we said, well, this is a chirality center because it has 4 different groups attached. It has a hydrogen, has a methyl group, has an amine, and it has this vinyl group. So because of that, there's 2 different ways you could build the molecule that can't be superimposed, and so you'd want to pay attention to that when you were naming it. We said for B that you have a chirality center there because you have a bromo group, a methyl group, an ethyl group, and then all of that. Those are 4 different kinds of things that are attached to that chirality center. And you look at groups rather than specific atoms, because an ethyl group is a different size and it would project differently than a methyl group. And you're looking at what might fit into a particular binding pocket in an enzyme, for instance. Okay, and we also said that this is also a chirality center, because when you look at that carbon, you have a bromo, an ethyl, a methyl, and all of that. So different groups. All right, for C, C is a little bit trickier. For one thing, if you have a cyclic compound, you always want to draw in any implied hydrogens that are needed to help you see what's going on. Every carbon has to have 4 bonds unless it has a positive sign on it, but we aren't there yet. So for right now, every carbon has to have 4 bonds attached to it. So if you only see 3, then draw in a hydrogen. If you only see 2, then you draw in 2 hydrogens. But then, of course, it can't be a chirality center. So I'm only going to draw in the ones that have the possibility of being a chirality center. Okay, so just looking at this carbon right here, it's easy to see that you have a hydrogen and a methyl group and that those are different from each other. The trick is, how do you evaluate the stuff in the ring that's attached to it? So what you do is you go around the ring each direction and see if it's different at any point as you're going around. So this has a CH2 here, and this has a CH2 here, and I'm sorry this is getting so cluttery, but... And then you come around here and you've got a CH2 here, but if you go to the next carbon over, it's a carbon with a chlorine and a hydrogen attached. So those are different. So that means those have 2 different groups attached to it. And so that's a chirality center.
But if we were to put, if there was a Cl on that, well, a 3rd carbon.
If there was a Cl here, for instance,
yeah,
then it's not a chirality center.
Then none of those would have been, well, other than maybe that.
The chlorines might be, yeah.
But that one would have been, okay. Makes sense.
Kind of, sort of. All right. Okay, and then I'll try not to garbage it up so much this time. This one is also a chirality center because you have the hydrogen, you have a CH2 and a CH2, but here you have a carbon with a CH3 attached to it, and here you just have a CH2. So that's 4 different groups attached.
So would you mind circling the 4 different groups?
Sure. Or no, I guess I wouldn't mind. All right, there's your hydrogen and the chlorine. And now when you're going this way around, you come to a carbon with a CH3 and a hydrogen attached. Okay. When you're going this way around, whoop, you're coming to a CH2. So it went CH2, CH2, so that's a tie, but you can keep going around. So then you go to the next one over, carbon with a CH3 attached. This is a CH2. Those are different from each other. So you just trace around evenly around the ring and see if there's any difference going each direction. Okay, so that one has 2 chirality centers as well. All right, the next one doesn't have any chirality centers because you can't have a chirality center if you have 2 or 3 hydrogens attached. And the oxygen doesn't have 4 things attached, so it doesn't have any. All right. C, don't bother looking at anything that has multiple hydrogens. So that means we're only going to be looking at this carbon to see if there's 4 different groups attached to it. It does have 4 different groups. You have an ethyl group, a methyl group, a propyl group, and a bromine. So that's a chirality center. F, there's no point at looking at the carbons in the ring that don't have anything attached to them because those are all CH2 groups. So that can't possibly be a chirality center. So you're only going to look at this one to evaluate whether it's a chirality center or not. This has a methyl group and a bromine. There's 2. But as you're going around the ring, I'm short. Here we go. As you're going around the ring this way and this way simultaneously, CH2, 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 CH2. It's all the same every way you go around the ring. So those aren't 2 different kinds of groups attached to them. And so that is not a chirality center. In other words, you wouldn't be able to build 2 models of that and not be able to flip them so that they line up. G, the only one that you're looking at as possibly being a chirality center is that carbon there, but the issue is that you have 2 methyl groups attached, so you don't have 4 different groups. So that is not a chirality center. H, all of the carbons have multiple hydrogens, so there's nothing to even look at there. And I, you have a CH3 has multiple hydrogens, so you're not looking at that. Any of the carbons in the ring have multiple hydrogens, so you're not looking there. And or they have a double bond. So those can't be chirality centers because you've used up 2 bonds on that double bond, and so that means they can only be attached to 2 other things. Yeah, so there's nothing there.
Now, when it comes to chirality centers, can carbons only be ones that are chirality?
No, but they're going to be the most common ones. So oxygen commonly wants to have 2 bonds, for instance, so it's not going to be a chirality center. Nitrogen commonly wants to have 3, but it could have 4 and have a positive formal charge. So it has a potential. But carbon is the one that really wants to have 4 bonds all the time, and so that's why you're kind of focusing on that. That's going to be the most common.
But if there was something else that had 4 bonds, it could be chirality center.
Yep.
Okay.
Yep. All right. So now I've gone through the problems, but I was hearing a lot of iffiness, is that a word, about them. Do you have any questions now still that remain?
It's just like the logic first. We roll out double bond or triple bond. And as long as the element is not attached to 4 different carbons or hydrogens, then if it's not attached to 4 different things, then it's not a chirality.
Right. Yep. And so that's why you can rule out also anything that has multiple hydrogens. Good. Okay. So today, what I thought we'd do is first off fill in the workbook page right before that. And then I want to show you how to represent 3-dimensional images on a 2-dimensional surface. so that you can figure out how to interpret it, and hopefully, no, there's no way in the world. Tomorrow we'll get into how to label the different types of projections for a chirality center. All right, so there are actually 3 cases where you have to describe the stereochemistry for a molecule. We're only working with the first one right now, but the first one would be is if you have a carbon that has 4 different groups attached to it, in which case it's a chirality center. As we go through the chapter, I'm going to show you 2 others, so if you can't quite picture it just yet, that's okay. This is meant to be kind of a roadmap, so you have everything organized for what we're doing, but I'll show you in more detail later. But if you have an alkene, and each of the vinylic carbons are the ones that are participating in the double bond there. If each one of those have 2 different things attached, not that they have to have anything unique between the 2 vinylic carbons, these don't have to be different, but within this vinylic carbon, if you have 2 different groups attached, this one has 2 different groups attached, then you have a possibility for different kinds of stereochemistry. It's not the same idea as a chirality center, so it's going to have different labels. But a double bond doesn't allow rotation because you have to have side-to-side overlap of p orbitals. So this is locked into place, and it doesn't matter how you flip this or spin it, it's not going to be the same as that. Okay, so if you have an alkene, and the vinylic carbons have 2 different groups attached, then you're also going to have to say something about what that stereochemistry looks like in the name for the molecule. That's 2.
Wait, can you repeat that?
Sure. The second case where you might have to describe stereochemistry is if you have vinylic carbons and each one of them has 2 different things attached. And that's because you don't have the ability to rotate the bonds, to line them up. The third case is if you have a cyclic compound with 2 different groups attached. Because bond rotation isn't going to be allowed in a cyclic compound either, at least not within the ring, then you're not going to be able to make those 2 match up. So a cyclic compound or a ring with 2 different groups attached, you're also going to have to describe the stereochemistry for it. Okay, but all we're working with right now is case 1 where you have 4 different groups attached to a carbon. We'll get to the other 2 later. Don't mix them up. As far as case 1, the condition that must be met for a carbon to be chirality center. Hopefully you got this one. 4 different groups attached to it.
Can't have a double bond, so I guess I can.
Right, so those are cases to make it faster for you to find it. The bottom line is 4 different groups, but what the thing that makes it easier for you to find it quickly, don't look at anything with a double or triple bond. Don't look at anything that has multiple hydrogens. That'll narrow it down really fast for you.
I guess.
Okay, and if carbon is part of a ring, how do you determine if it has 4 different groups attached to it? So I'm most specifically using this as an example. Okay, and you can put in your own words, but essentially what you want to do is go around the ring and compare, and if you come to a case where you have 2 different situations, then that's chirality center, as long as these 2 are also different from each other. So that is a chirality center here because you have a bromine, hydrogen, and then as you're coming around the ring, CH2, CH2, and then you have a CH2 carbon with a double bond. That's different, so you've got these two groups are different from each other also. So you just have to compare all the way around. If that's not workable for you to just trace around, the other thing you can do is just mentally clip this and write out the sequence for that. And then go back and mentally clip this and write out the sequence for going the opposite direction around the ring. And see if the two match up. All right. So I already had kind of told you about what hatched line and wedged lines mean and all of that. Let's go through this though. There are two different ways to represent a three-dimensional structure on a two-dimensional piece of paper. One is called a perspective formula and the other is called a Fisher projection. They both have their strengths and weaknesses. There are going to be cases where you want to use one versus the other, but the bottom line is that you want to know how to work with both kinds of representations because you're going to see both. So a perspective formula is one where you have the wedge, the solid wedge and the hatched wedge to represent things coming towards you and going away from you. So for instance, if I was going to draw this three-dimensional image on paper, you've got these three atoms are all in a plane, and then you have one sticking out towards you and one going away from you. So you write the ones that are in a plane just using normal lines. The chiral carbon is usually not written in, it's just implied by that junction right there. And then whatever's coming towards you is a solid wedge. And then whatever's going away from you is a hatched. Because when things go away from you, it looks less clear. Right? So if you had the green and the red and the orange and the white, like that, that's how it would be written to represent that kind of structure. So, for your notes, the lines are in a plane, in the plane of the paper. Solid wedge is coming towards you. And the hatched line is going away from you. I just want to make sure that you're clear. I usually write it with hatched and solid wedges on the right side of the molecule. I think that's just kind of like how it's usually represented, but it's perfectly acceptable to also represent it like this. You know, it doesn't have to be that same structure that I'm always drawing. So this representation is going to be more useful if you have to kind of see what the stereochemistry looks like. It's easier to picture what the stereochemistry is than a Fisher projection. So this might be more useful, for instance, if you're doing a reaction mechanism and you're trying to picture what's going to happen. A Fisher projection, I kind of call it a fishbone projection, even though it doesn't have anything to do with anything, but that's how I randomly remember. You might see in biology books or biochemistry books or something like that where it's talking about a complex structure that has multiple chirality centers. For instance, a carbohydrate. And with a carbohydrate, then they're representing it like this. Each one of these is a chirality center. And this is a whole lot easier to represent than all of the different things that are coming towards you and going away from you. So a Fisher projection is easy to draw, and that's why you might use that. It's harder to interpret. You have to pay really close attention to the rules for what everything represents. So for a Fisher projection, instead of having things in the plane of the paper, you've got two of the groups coming towards you and two of the groups going away from you, like that. So only the carbon is in the plane of the paper. So in the textbook, I represent this, or I kind of try and help you picture this as though you're at a family gathering and there's a 3-year-old child there, and one of the women says, "Oh, come here to Grammy and give her a kiss." And the 3-year-old's like, "Ah!" And so, they'll kind of like, oh, they're going to give her a hug, but it's like, "Oh, please, no, not that." It's kind of like this. See, it's got its arms out to hug you, but it's kind of like, "Oh, please don't kiss me, please." The vertical lines have to be going away from you. The horizontal lines have to come towards you for a Fisher projection. So, for example, if a student hasn't had organic chemistry yet and they're taking biochemistry, and they see this and I say, "Oh, well, one of these this is glucose." Oh, wait, you guys some of you have had biochemistry. What's that one? If I fill this part in, of course, but the chirality center's here. Galactose, very good. And so they always go, "Well, now, why can't I just take this and just flip it around?" It has to be coming towards you. If you rotate it around, it's going away from you. See, so that's why it has to, that's why these are different from each other. Yes, bond rotation is allowed in a molecule with single bonds, so it could rotate. There's nothing stopping it. But for you to represent it as a Fisher projection on paper, you have to orient it in this specific configuration. And so those mean different things. All right, I've got a couple of announcements really quickly before I turn you loose. One is that Dr. Goolsby from VCU Dental School is coming to Washington and Lee to give the presentation for VCU Dental School. She'll be there on the 19th. But she said that she is willing to meet with any pre-dental students one-on-one. And there are going to be appointments every 20 minutes starting at 3:30. So 3:30, 3:50, 4:10, 4:30, 4:50, and 5:10. I've been told that you need to send all of the appointment times that might work for you, and they will schedule a one-on-one meeting with her. So if you want to meet with the person who's the head of the admissions program at VCU Dental School, let me know. And when you go and meet with her, it might be helpful for you to bring transcripts, grades, a list of your extracurricular activities, your involvement with RAM, all that kind of stuff. She'll help you figure out what you need to do to become a successful applicant. Another quick announcement for you. Let's see. We have a person coming who's head of admissions for an anesthesiology assistant program, which he was telling me about what it's like to become an anesthesiology assistant. And I thought, is it too late for me to go back to school? Great hours, great pay, fairly short graduate program, high demand. I was like, whoa. Anyway, he's coming here on Thursday afternoon or evening. He's willing to meet either one-on-one or as a group. I'll talk to you tomorrow about what time might work better for your schedule. And then there's one more thing. Oh yeah, the RAM clinic coming up a week from this weekend. Apparently there's quite a few people who want to go, but nobody who can drive. So if you're interested in going and would like to be a driver, you're moved right to the head of the line, so let me know. Or if you can qualify to become a driver, even if you're not a driver currently. It's not that difficult, huh?
At least 21.
You have to be at least 21, that's right.
Okay, I was just going to ask what you have to do to be a driver. So.
Yeah, so it's just you take a little test, don't you, online or something?
You just have to go talk to, I don't remember his name because I didn't have to register this year, but all you have to do is go talk to a guy now who says, "Show me your driver's license," and you're good to go.
Oh, all right, even easier. All right, no homework for tonight. We got to work with a bunch of stuff first. See ya.